I have two papers. I wanted to comment a little bit about the algorithm session. The planning committee, the organizing committee had a lot of discussion about the relevance of the algorithm session. And we are acknowledging the fact that as data processing and the amount of data we have to have increases, smarter algorithms are required. And it's very important to the CTBTO enterprise to be able to process data in an efficient way that sifts through that data to provide accurate answers, as we've seen so many cases during this meeting. So we believe the importance of the algorithm session will increase as time goes on, and that's our hope. And we have two presentations today. So I'm going to introduce Hakim Gadou, and he will present the first paper on enhancements to the CTBTO IDC radionuclide processing pipeline.
Thank you. Good afternoon, everyone. This work is about the enhancements to the IDC software for radionuclide data processing and the way this helped improving the quality of automatic results in the pipeline. The current IDC software for radionuclide is relatively new. This has been deployed in IDC operations only in June 2011. And this is fully open source, in-house developed software. The pipeline includes the automatic modules for both particulates and noble gas data, then interactive tools for the analysis of the two technologies. So this is the way the particulate samples are categorized over a 5-level scheme. Level 1 and 2 correspond to background detections within or above the abnormal limits for the station. Then we have 3 levels from 3 to 5 in case we have a CTBT detection. After improving the quality of reviewed results over the first year since the software has been deployed in IDC operations, we changed the focus to start also improving the quality of automatic results. And the aim was also to reduce the workload in interactive mode. Everything started with the retrospective analysis, where we took a closer look to 20,000 samples over the year 2014. Then the aim was to identify the most critical areas that need further improvement. And this was the outcome. Out of the 20,000 samples, we realized that we had 11,000 false peaks, which means almost a false peak in every second sample. Then 33,000 false positives in terms of nuclide identification, which correspond to an average of 1 false positive per sample. On top of that, there was also some misidentification because of radionuclides in the background. On top of 2 critical CTBT, anthropogenic for cadmium-109, then technetium-99, which needed some different treatment. Based on this, we identified the software solutions for reducing this rate of false positives and then improve the quality in automatic mode. Those are the 6 major areas where we implemented improvements over the 2 last years which means we have been working on one software solution every 4 months. The first one was to optimize the key lines of 7 major radionuclides. Then the second item, it's the chronology is from left to right. Then we automated the handling of false peaks. Then we implemented an automated module for discriminating between technetium-99 metacable and germanium-75M. Then we further updated the radionuclide library for natural radionuclides. And then recently we implemented an automatic background subtraction for particulates. And the latest change so far was to optimize the configuration for fixing the baseline in automatic mode. This is, for instance, the way the radionuclide library has been updated for those major nuclides in terms of key line. As the old way those key lines have been identified was to just use the most intense line for each nuclide. Then this ended up in too many interferences with the natural radionuclides, and because the software is per design, was behaving in a safe way, then those nuclides are kept in the automatic mode identification, and it's only interactively that analysts have to filter that out in manual mode. Then this is now the new key lines that are taking the first criterion into account, but not only that, which means the way these new key lines are defined also takes into account the potential interferences with the natural radionuclides. And then, of course, by doing this, we also made sure that the impact on the detection sensitivity will not be affected in a compromising way. And this was the case for all those nuclides. Actually, we even had one case where the MDC is a bit better compared to the previous key line. Then we had the additional nuclides where the fixing the key line could not work. This is the case of technetium-99 metacable, which has only one gamma line. And by chance, this gamma line is within the interference window to the germanium-75M line. And by chance, this is the only line of germanium-75M line. And then, actually, this is not the algorithm. It's not new, but what is new is that we moved this from the interactive analysis side to the automatic mode. And basically, the idea is to cross-check the peak around 140 keV against the second peak, the peak from the second germanium isotope, and then decide in automatic mode whether this is more likely to be technetium or rather just germanium, taking into account that the two germanium isotopes have the same cross-section in terms of production rate. They also have very similar emission rate, and then the two energies are also close to each other, which means the detection efficiency is also very close. And then by doing this, then we needed to define a threshold for the algorithm in order to take the decision. And then we considered a couple of values between 1.5 and 1. And finally, we decided to go for 1.1, which means something like more than 90 5% of the cases would be screened out already in automatic mode, and the 5 remaining % of cases would provide a very safe margin so that we don't miss any real detection. This is now So this is now the way those changes. It's just a couple of examples how the situation started improving by implementing those software enhancements. The first plot is for the in terms of reduction of false positives. And here you see the monthly total number, which dropped from around 350 down to 30 cases, which means a reduction factor of 85%. And we, of course, kept monitoring that no real detection of technetium 99 metastable has been missed by implementing this in automatic mode. Then for those 7 key radionuclides, the reduction factor is about 93%. This is the fraction of false peaks that are now being handled in automatic mode, the blue part. This is how the implementation of this automatic background subtraction improved the results. This is the Takasaki station in Japan, which is still contaminated from Fukushima fallout. And before implementing the change, we have been detecting more frequent, we have been reporting more frequent level cesium-137 at higher numbers. And here the improvement was in both in terms of reporting frequency, but also in terms of activity concentration, as only the net contribution from the filter is reflected here. Then we revisited 11 level 5 spectra from 2013, and we did the reprocessing in offline mode by subtracting the background contribution. And then we compared the new IDC results with the certified laboratories of the IMS. And here we compared to the average of the 2 laboratories in order to decouple some extra issues. And the results are perfect compared to the situation before, where up to 40% discrepancies have been reported before starting doing this in automatic mode. Now, in terms of bigger picture, this is from January 2014 until the previous month, May 2017. And on the y-axis, we have the number of false positive, just in normalized mode. The big picture is that we are now reporting 70% less false positives in automatic mode. And then here you see how this is well correlated with the different software enhancements that we started implementing in February 2015. Here is now the share of the 5 categories from January 2014 until now. And as you can see, we started with 20% of level 5 spectra. And now it's only a few cases taking into account that this is in automatic mode, which means we now started having more open sky compared to the situation before. This is now combining the software improvements with the better staffing situation in the IDC operation. This is the timeliness, which means the delay between the automatic processing and then the production of the reviewed product, RRR. In 2014, we had actually just the summer backlog overlapping with the winter backlog, which means we had almost 8 months of a high backlog up to 20, 30 days of delay. Then the situation started improving here. This is the peak for summer 2015, where we didn't almost have any peak, any backlog over the winter break. And over the last year, we had almost no extra backlog at all. This is now the rate of consistency between automated results and reviewed results, which is one of the key performance indicators of the IDC. It's the last slide. And here, we improved the situation from 40 up to 80% for if we combine noble gas and particulates, which largely exceeds the target limit of 55% for the 2 previous years. So there's improvements has positively, of course, affected the quality of automatic results and then significantly reduced the workload on analysts in interactive mode. That's all. Thank you.
We don't have time for questions, but we have time for discussion, yeah, a bit. And the second presentation, thank you. And the second presentation is by Professor Richards, and he returns us in the world of cross-correlation with LG wave. Please.
Thank you. So I am here to report on a research done over several years at Columbia University, most recently in a collaboration between Columbia and the Sandia National Laboratories. And broadly, as you see from this title, it's actually about one of the oldest problems in seismology, namely, how do we locate earthquakes and explosions from their seismic signals? Well, actually, you don't get that from this title. The title's got 19 words, so let's simplify it a little. So this talk is really about precision seismology, as in some cases we can do it today, and as I very much hope the community can do it in the future. So this is my succinct phrase instead of that long title. And what I want to talk about in the next few minutes is some of the steps we have taken over a period of about 10 years that contrast with the traditional method by which earthquakes are located, which goes back more than 100 years to 1912, when the Geiger's method was introduced to locate earthquakes one at a time with phase picks using some model of travel times. This talk is mostly going to be about earthquakes in China, and from this old map you see that earthquakes occur pretty much all over, although there's an exception in this region. That's the one exception, and there's on the order of a few thousand earthquakes a year in this region. With David Scharf, my colleague at Lamont, more than 10 years ago, we found that more than 10% of these events in China turn out to be repeats of each other. Repeats in the sense that for a regional seismogram, over a period of a few hundred seconds, in the present case there are actually 2 seismograms, one on top of the other, one in red, one in blue. The strongest wave, the one that's the focus of my talk today, is the LG wave, which is an interference of shear waves in the low velocity crustal waveguide. And the point is, as we investigate this phenomenon of very similar seismograms, how many of what fraction of the seismicity of a broad region has this repeating property, and if the seismograms don't quite repeat, how well can we use the whole waveform to get relative locations? So to give a little more detail of that seismogram, we see it's very hard to pick the P arrival, so methods based on P wave picking have an intrinsic problem. Again, there are two seismograms on top of each other here, and when we have this degree of coherence, the same signal passed in the band between 0.5 to 5 hertz, a long time bandwidth product, we would have to say that these events have to be within 1 kilometer of each other. And one of the early things we did was to see how far apart these repeat earthquakes are reported to be in traditional bulletins when they're located separately. And I don't want to make too much of this, but it's one of the worst examples where in the annual bulletin of Chinese earthquakes, the seismogram from the earthquake that is written here in red was reported with a location 142 kilometers away from the location of the seismogram shown here in blue. So I reported more than 2,000 pairs of repeating events to Professor Wu Zhongliang some time ago, and with his students, he took this set of more than 2,000 doublet pairs and made maps with his colleagues, notably Changsheng Jiang, and mapped how far apart are these repeating earthquakes. So this was published a few years ago on the map of China, where you see in blue then the pairs of repeating events are on the order of only 5 kilometers apart when reported in standard bulletins of Chinese seismicity. Where you see red, these are less well documented earthquakes whose location, which from the repeat seismogram we know has to be within 1 kilometer of each other, can reach up to 35 or 40 kilometers apart. So this work was all done several years ago, and broadly speaking, for a 21-year period, more than 2,000 repeating pairs of events were found. On this map are shown in green more than 300 stations, mostly temporary stations, for which waveform data is available from the IRIS consortium. Shown in yellow are a very small subset, I think about 14 stations, which have operated for a longer period of time and captured 33% of the seismicity for the 21-year period we studied in detail. And broadly speaking, where you see circles, these are places where repeat earthquakes were found by us to have occurred. But today, with this background, I can get into the question of where actually are they, and can we get relative locations of these events? So to that end, this, roughly speaking, is a quick summary of our results. The events in blue are the relocated earthquakes. Most notably, I'll point out from the blue, subsets in white. So there's one huge cluster of more than 700 events here in the West. And then I'll say something special about studies led by Megan Slinkard, but also with my colleague David Scharf at Columbia in a study of Wenchuan aftershocks. So what was done was to carry out over 100 million cross correlations of the 50-second LG window and to measure the time corresponding to the maximum cross correlation estimated with subsample precision by fitting a parabola to the 5 points nearest that spike in a cross correlation peak, and then to take the data of all the measurements of the relative arrival time measured from the LG wave for each pair of events that were recorded at a sufficient number of common stations to get an estimate of the relative location. And the broad result that I wish to convey in this short talk is conveyed in graphs like the present one, where I now need to explain that each row is a summary statement about a particular cluster in the previous map. And now let me describe what you see in each column. So here is a statement about 6 separate clusters. In this column, if you have good eyesight, you can see that this is plus or minus 10 kilometers east-west and north-south as a map of the location of events in a traditional bulletin. Immediately adjacent is our relocation of this set of events into a tight cluster with the same spatial scale. The first column is the same relocation, but now with an expanded spatial scale, so it spreads only over plus or minus 2 kilometers. And then this is a column about confidence ellipses, which I don't have time to go into. And on the far right are shown some of the global moment tensor solutions giving the focal mechanism for events in the cluster. And what is of interest, certainly to me, is, for example, in this cluster, which is from Liaoning province, we see a rather scattered set of events that relocate to a tight cluster, that when this tight cluster is plotted with an expanded scale, shows a sense of linearity which conforms to an overall moment tensor conclusion, and one would choose this as the relevant fault plane. So I can show this for another set of 6 clusters, and another set of 6 clusters, and another set of 6 clusters. Broadly speaking, we found 100 clusters in the seismicity of China with 5 or more events, and our summary statement would be as follows. Precise location for about 4,000 events for a 20-year period, which is about 20% of all starting locations, and a huge reduction in residuals. And the confidence interval puts this with some degree of confidence. These are locations, not absolute, but relative, at the scale of a few hundred meters. So that's cross-correlation in the context of event location. Work led by Megan Slinkard on the aftershocks of the Wenchuan earthquake, a tragedy of May 2008, is shown here in map view. In this case, 3 stations, Xi'an, ENH, and Kunming, were supplemented by a small number of temporary stations from the SnT project. Were used from the archive of each of these stations the waveforms of about 1,400 known aftershocks for a 100-day period, which were then run on a channel-by-channel basis to see what additional events were detected by cross-correlation now used as a detector. And traditional bulletins show in either blue or black the number of aftershocks found as a function of time, but in red, by this method of cross-correlation detection, about 5 times more events. Shown in this way, the red are the templates used to detect in blue the additional about 5 times more events, and then to relocate everything is shown here, a diagram somewhat similar to one I showed before, again with this concept of events being located like this, one at a time, but actually the aftershocks are clustering. This is with the same spatial scale in these 2 maps. So these are our clustered locations, shown here with an expanded scale and shown here with their confidence ellipses. So, to apply modern methods, this is what I would like to see happen and I don't know, frankly, which institutions will take the leadership to do this on a large scale. To apply modern methods, there are 6 steps of identifying seismic events likely to be well recorded and to be made the basis of templates, to cross-correlate the template against a continuous archive, to validate detections, preferably by, well, there's a number of different ways to do that. To measure relative arrival times via cross-correlation of pairs of events, and to relocate as many events as possible using double difference. So broadly speaking, I see this as the new telescope in our field. I have talked about our work. Many people have contributed to this. It's almost a cottage industry. If you want to do serious quantitative seismology today, many seismologists have come to their grief to learn that they need to do relocation by modern methods first. I would love to see that work done more institutionally for the community. The work, I think, mostly initiated in Iceland in the 1980s and 1990s and has been contributed to by on the order of 20 different people. Who should supply these results for the community? I don't know, only time will tell. But wherever LG waves can be found, it's pretty clear now the decisions that need to be taken to allow 100-fold improvement in the precision of locating seismic events. So this is of importance far beyond treaty monitoring issues. It's probably of greatest importance in the greatest problem of seismology, which is to achieve a deterministic interpretation of a catalog of seismicity. How can you see when one earthquake will influence the next earthquake if you don't know exactly where all these earthquakes are? So I'm very excited that over a period of time, we've gradually achieved this degree of improvement.
Let's thank our speaker. We have a couple of minutes for questions prior to the folks who are needing to give the poster, 1-minute posters, if you could line up on our left-hand side over here.
Paul, I found that fascinating. I was wondering, did you ever see anything other than doublets? Did you see triplets?
Oh, yes, indeed. And so the biggest one was 719.
Fascinating.
Yeah.
And do you think a Kepstrel approach would be of any use in the analytics?
No. So this has used the whole waveform. Kepstrel approaches very useful for a number of projects, but here we're just using the whole waveform, and there are questions about going with spectral methods to improve the work of doing cross-correlation on a large scale, but the Kepstrel methods are intrinsically nonlinear, so that's why I gave that short answer, negative.
It's fascinating work.
Okay.
We have time for one more question for either Dr. Godot or Dr. Richards. There's one way in the back there.
Hi, my question was for Hakeem. The updates you've done for the automatic processing for IDC radionuclide analysis, are they going to be, or are they already, have they been put into the NDC in a box for NDC use as well?
Yeah, thank you for your question, which actually I forgot to highlight that all those improvements are already deployed in the NDC box. And the latest was in the release that we produced in April last month, which includes the background subtraction, but also optimized the parameters for the baseline. And this is indeed a good thing, which means thanks to the fact that we are operating fully open source software, which means we are also providing the same within the NDC box software package, and any improvement to the IDC operations is systematically brought to the into the box as well, with a couple of months of delay. That's all. Yeah. Thank you.
Okay, next we need to progress. We have a total of 8 posters, And so please begin with the first speaker. You have a minute as soon as the poster comes up.
Hello. We apply an advanced machine learning technique named diffusion maps. My colleague will describe it in several minutes. Our automatic classification is performed in at three different scales. First, discrimination between earthquakes and explosion in classical way in some area. For example, we have achieved 95% correct discrimination in Dead Sea area. In the lower scale, we use this method in order to identify and separate different quarries. And last, we use this method for discriminating anomalous explosion on some quarry, specific quarry. Thank you.
I'm Megan Slinkard. My coworkers and I used waveform correlation to monitor a large region of Eastern Asia. We use this study as an opportunity to explore some of the challenges in doing automated waveform correlation. How do you select your templates? How do you set thresholds for those templates? How do you validate results? And what are the computational requirements for doing this on a large scale? We use several thousand templates because we drew our templates from the entire station history, which was sometimes up to 25 years of data. And we did an entire year of continuous waveform processing on 12 stations. Our results were analyzed to look at the impact of history, template phase, and network density.
Thank you. Next.
This is about waveform cross-correlation again, but now it concerns two mines, the Kiruna and Aitik mine, measured by IMS stations, NOAA, FINES, and ARCES. So we developed a set of best templates related to master events at Kiruna and Aitik and make automatic processing with detection, association of phases into REB events. REB means three primary stations involved with the good detections and relative location of all that events. You can see that the current REB for Kiruna Aitik have the aperture of 20 to 30 kilometers for the events which are in one point within 1 kilometer. So we also demonstrate that the location is within a few hundred meters for the events which are presented. Thank you.
Okay, next. Thank you. Okay. Okay, can you go back one? Okay.
We are using array processing, we're investigating Melkepstrom, and we are discussing integration into our algorithm, and we invite you by our poster. That's it.
Okay, thank you.
Thank you.
Okay, so this is related to poster number 3 that was presented here. We review diffusion maps, which is a nonlinear dimensionality reduction technique. We apply it to create a compact model for seismograms for a certain region. The advantage of this method is that we are able to preserve the geometry or some physical properties in the low-dimensional model. That is better than maybe linear models like PCA, which create a compact model but do not ensure to preserve the original geometry of the data.
Okay, thank you.
Hi, good afternoon. I'm Boxue Liu from the IDC of CTBTO. Yeah, our post is about the peak search and fitting analysis for the radio Xenon beta gamma coincidence and spectrum. This peak search and fitting method is based on the concept of the Q-rate detection limits. The peaks are searched by using the three curves of the baseline, RC, and the single channel analyzer. So, this, okay. Please, it's over. Okay, thank you.
Okay, thank you.
I didn't recognize it, the last one. So this is about the waveform cross-correlation again, and now it uses the data not only from IMS stations, auxiliary IMS stations, but also from the stations from Sorek, from Israel. So they merge data and relocate events in phosphate mine in Jordan. They also use the methods of dimensionality reduction and subspace detection to improve the detection level and the level of relative location of the events, which should be very close to each other by definition because they're in the same mine. But they also have a scattering of 50 kilometers, even if the stations are very close to the mine. So the cross-correlation, waveform cross-correlation improves location by 2 orders of magnitude, together with estimates of magnitude, of relative magnitude of that events. Thank you. And I would like, because we're closing the session now, yeah? I have just one remark. I did not recognize how much algorithms improve this world. And today we talk about the improvement by 95% and by orders of magnitude. And this is just algorithm. It is not new data, it is not the new theory. This is how we process data. And thank you for joining this session. And I think it will be evolving in time and showing best and better results. Thank you.
Thank you very much. Are there any last-minute questions we have about a minute left before the next session. We have one hand in the back, or have two other questions for any of the speakers. Do we have microphone?
So this actually is addressed to Hakim. Hakim, is a very simple question and fast one. Can you comment on how the new approach, I would say, is dealing, if any difference, regarding the minimum detectable limits?
Mm-hmm. Do you mean actually, by the way, maybe it's not within this session, but we have another poster which is dealing with such a topic, and that's something we implemented within the spatial analysis after DPRK tests in January. And the idea was to just sum up the particulates, the sample spectra within, of course, which with the assumption that they are intercorrelated in terms of source. And by doing that, we got some improvements in terms of MDC, of course, which by summing two spectra, we could reduce very roughly by a factor of square 2, which means 1.4. And we also extended that to particulates, and this improvement in MDC has also been confirmed. Yeah, and that's under the session, I think 2.1, and the poster is standing in the corner of this small room, the Wintergarten. Thank you.
Thank you very much. That concludes this session. Thank you to my colleagues. I appreciate all the speakers.
Okay, I was going. Your name is? He will announce you, so.
Italiano? Plastino. Questo è un nome in italiano? Allora, nome ok, capito.
Are you okay with sitting here, or you want
No, I think that you should be that you will be here. I will be here because I'm going to take the notes of the. You give card and fight here. I will do that tomorrow. Don't worry.
No problem.
We can't do this. No, we will be here.
Okay. Okay.
Can you first join us here, please?
Yes.
Yeah.
Not here?
Yeah. You'll move here when we. The talk is there, but you will sit here till we launch. Good afternoon, everyone. Also those of you that joined us since the end of the previous session on algorithms. My name is Gerard Graham. I'm the coordinator in the IDC, and chairing the session with me is Gerard Rambola Manana from Madagascar. We have two speakers this afternoon. Then we will have 15 minutes for discussion, and I believe we have 57 posters in our session, so it may be a surprise to all of us as we start lining up, but I will call all of you that have 1 minute preview slides closer to the time, and then we will see what are we in for in terms of time at the end. So without any further announcements for the time, let me hand over to Gerard, who will announce the first speaker. But before I do so, also I would like to invite the second speaker to please join us up here, please. Thank you.
Okay, the first presentation will be done by Dr. Plastino Wolfgango from the Roma Tre, Università degli Studi, about the predominant Xenon time series analysis, a new methodological approach for ATM at small synoptic and global scales.
Thank you, Mr. Chair, and let me thank the organizer for giving me the opportunity to present this methodological approach that we developed in the framework of this virtual data exploitation center collaboration, in the framework of a collaboration agreement between CTBTO and my university. And so we tested our methodology and on the PTS data, and specifically to try to support and improve the CTBT event screening categorization. And in our our idea is, of course, that we need to start beginning on the preliminary characterization of the IMS station as receptor, of course, in terms of backward modeling, or as source in forward modeling. And we tested this approach for beryllium and xenon data, and of course, checking also the meteorological data at MS station. In the reality, you know that the problem is complex because, of course, we have not a single source in the case of backward modeling, or in terms of receptor when we have not a single receptor when we are modeling in forward. But anyway, the tentative is to characterize this relationship between a source and receptor, and characterizing this matrix sensitivity matrix. And once again, the experimental data that we have at receptor when we are looking and we are performing backward modeling, or is a source when we are performing a forward modeling, but anyway, it's our IMS station. So the idea is to screening and to try to characterize all possible structure in the signals detected by IMS station, and we follow these procedures. Of course, the formula, but I explain in a few minutes the flow chart. So we process at the beginning the original data, and we use this generalized lobe Skergel spectrum to identify all the periodical contribution in the original signals. And of course, it's very important because I will show later. The periodical component is, of course, not a steady-state component in time for all period of investigation. After that, of course, we have a residual time series, and we would like to analyze the structure of the residuals and, as possible, to identify the noise structure, because before to perform a cross-correlation or to compare data between a station, or to realize a model, a global model in terms of ITM, in our idea it's important that we know each characteristics in the signals detected in each IMS station. So, of course, we use the goodness of fit test. In that case, we use Kolmogorov-Smirnov and Anderson and another test to check the distribution of the residuals. Then we normalize and we define the outliers. But to study the persistency and the probability occurrence of these outliers, we use also the trend and fluctuation analysis. This is an extension. In that case, it's possible to define this local Rast exponent, and we can characterize in the residual time series the noise structure. If this parameter is in this range, indicate a long-range correlation, this means the white noise is the parameter is equal to 1, is equivalent to pink noise, and of course is equal to 1.5 is correspond to Bronner noise, so rate noise. So the cross-correlation is at the end of this process, and we cross-correlate the residuals. And once again, if I compare this information with the meteorological data, can give me an information if the outlier or the so-called anomaly is really related to, for example, a nuclear test or nuclear accident or other physics behind. This is the analysis that we performed for about 13 years of the data provided by PTS for beryllium. You are indicated the carrier. These two symbols are the periodical component in the original signals, and this is the residuals. Of course, I will show in detail, but you can see by the different color and the percentage of each component in the original data that we have sometimes some similarities at regional and continental scale. For example, if I see Oceania, you have the similar colors for Australian station or New Zealand station. But this is a snapshot for overall time series. If I analyze specifically the component and at 1 year, I reduce the station, and but if I analyze in time, this is the plot that I try to explain. You have in abscissa the station, and you have the time. So this is the periodical component at 1 year by year, are change in amplitude and phase in each station. So seems from this snapshot that we have some similarities in this station. But if I look year by year, for example, looking the New Zealand station, this one and another one, you can see that we have variation in amplitude as well in phase. This line separates the southern hemisphere to northern hemisphere. This means that, of course, we need to consider this change, these dynamical properties of in the signals in the time series. This is the analysis for Xenon, available on 4 stations. And if I reduce once again the interest for periodical component to 1 year, remain only the Swedish station. This is Stockholm. But you can see that we have similarities for all stations in Xenon in terms of periodical component. Indeed, for time reasons, I skipped the similar plot that I showed for beryllium, because for Xenon we have no change in the amplitude during the years as well for phase. This is the air temperature for the same station, and you can see with different color that we have no similarities at local, regional, and global scale. We have different patterns for each station in terms of contribution of periodical component, as well as for the phase. Once again, if I summarize the information year by year for 1 year component, periodical component, you can see that we have variability from station to station in terms of percentage or amplitude content in periodical signal as well for phase. This is air humidity, and once again, it seems that we have no similarities in terms of local, regional, and global scale. And if I analyze once again in terms of changing time of the periodical component at 1 year, you see that we have some differences between stations. And of course, white line separate once again southern hemisphere. This is southern hemisphere to northern hemisphere. This is only the analysis from the original data for periodical component. If now we analyze the residuals and the noise structure, I selected the Swedish station, Stockholm, because it covers all the information in terms of beryllium, xenon, and meteorological data. And you can see that also the threshold, this is white noise, pink noise, red noise. And this is the pattern of beryllium in a Swedish station. And this is the pattern of noise of xenon in Stockholm, as well as for high temperature and high humidity. This, of course, is information. The next plot gives another information. This is the mean value of the Earth exponent. So I showed before the dynamical pattern of this parameter. This is the mean value year by year. And once again, you see that clearly we have a difference between beryllium and xenon. It's clear because we are looking about particulates and noble gas. We have, of course, different physics in terms of transportation. But it's clear that if I look only the xenon time series, you have this sigma and this expected value. Finally, when we have all this information, we can try to identify the so-called anomaly. This is the residual, and of course, we removed the all periodical component. We characterize as possible all the structure in the residuals and noise. And you see that always for Swedish station, for Stockholm, this is the pattern of residual, and this is the threshold to 3 sigma for beryllium, xenon, temperature, and humidity. It's not enough at the moment to state that maybe this is an anomaly. because maybe also a random fluctuation or resonant effect in a noise component, in residual noise component, that coupling, for example, the meteorology with our radionuclides. To confirm or not this hypothesis, we finally consider this cross-correlation, but the cross-correlation, this is not typical cross-correlation. This shows, for example, that if you perform the trended cross-correlation, we have not coupling between the Xenon signals and meteorological parameter in Stockholm. So this means that the probability that the spike-like that we observed in the residuals above the 3 sigma are not related to local meteorological effect in the station. For beryllium, we have no peaks, so spike-like that can be considered, so few that are above this threshold, but it's no similar structure for xenon. But, of course, these peaks may be related or can be affected by this correlation, inverse correlation with the humidity. So, in time, in conclusion, our point of view is that to perform atmospheric transport modeling, it's necessary a preliminary characterization of AM station by local meteorological patterns. And of course, this is a local scale approach. And for forward and backward modeling should be based on preliminary characterization of each relationship between IM station from local to global scale. And finally, the source receptor modeling should be normalized to local and versus local global scale approach. Let me cite the original source of this work is the rerum natura Titus Lucretius Carus, accidere ex una scintilla incendia passim. Thank you for your attention. I need to thank, of course, the PTS staff for providing the data in the framework of this agreement with my university. Thank you for your attention.
Thank you very much. We will get back to questions during our discussion session. We will now move on to the second presentation. This is by Justin McIntyre, SnT, a proposed platform for analysis of international monitoring system radionuclide data sets. Thank you.
Thank you. My name is Justin McIntyre. I'm from the Pacific Northwest National Lab. And I feel a little inadequate. I don't have a single equation in this presentation. However, with many of the things that we've seen at this conference, a lot of great analysis is being done. My talk today is about taking that analysis and trying to put it into a framework and a platform that allows others to generate up modules that can then be used by others. And so it's trying to create a community of experts that are generating up modules that others can use, benefit from both the research that has been done in the past, as well as folding that research into a community effort so improvements can be made. Let's see. I always screw these up. Okay, so I just start with advanced radio xenon analysis needs, and these are things that have come up. I've spent my career doing radio xenon analysis, and the development of systems, the algorithms, the physics, the science, and at each one of the steps that we started off with, first we get a spectra, we analyze the spectra, and it's great. It took days to analyze the spectra, figure everything out, and then you develop a system, and now you're getting spectra 4 or 5 times a day. You need something to develop. You need to develop a system that allows you to now analyze all that spectra, and it has to be automated so that you can look at all your great data. Then you start developing a system that's continuing to send data your way, and then you do a network, and even more data, and even more data, and even more. At each one of those steps, you begin to see that there's new science that is available to you if you can take the data sets that you had before and analyze them in a way that makes sense, and then work on the new stuff. And at each step, we've continued to make those advancements throughout the community. So for Radio Xenon, there's been a number of improvements from the Stockholm Equations that were done in 2001. We all had to get into a room. We were told that we couldn't leave until we came up with a consistent set of equations to analyze the data, and that was Joachim Schulze, who demanded that. These are some of the other things that have come along. Silicon detectors is kind of a big thing today. Great resolution, no memory effect. It comes back to this order of magnitude increase in sensitivity that you really love to see on a revolutionary scale. And so we're just at the cusp of that. Talk about high purity germanium. Other things that have come along that not quite so fascinating, but high purity germanium in coincidence with silicon detectors. That's 2 orders of magnitude in sensitivity now. Finally, we get down to the bottom bullet point, and the Radio Xenon data sets. We need data quality and data control, and that's something that nobody really likes to do that. We all do uncertainties. We understand that uncertainties and uncertainty bars and data quality is extremely important, especially for an operational system. But it needs to be automated, and it needs to be done in a way that is in the background so that when a question comes up, an audit comes up, the president calls, you are confident that the analysis that you have done is the best analysis that could be done, and you have the proof. All right, so that goes into SnT. We had to call it something. So the goals of SnT is a software platform. We start off with just the Radio Xenon data analysis. Hopefully if this goes well, then we can start adding in the particulate analysis to the community as well. What we want to do is be able to incorporate the expertise that's been developed over the past 20 years through a number of different working groups and organizations, the IDC, of course, being at the forefront of many of these things. We also want to make sure that we develop a platform that's flexible enough for future IDC needs as well as the NDC needs. So the NDCs go off, they generate something, they should be able to have a say in how the software is developed and deployed, as well as making those improvements for others. The big point is just provide a common programming platform for developers so that everybody understands that they're going to develop something. Tools will be made available that allow you to do something such as, say, plot or do a Gaussian fit. And these tools are all there, the calls are all there, what you need to supply is there, what gets returned is consistent across the board. That's really kind of the backbone of SnT. And of course, at the end of it, maintain a consistent data analysis experience for the IDC and the NDCs as well. They've been doing this for decades now. We're not going to change everything. All right, so then we go into just the platform description. This goes through some of the technical details that within a couple of the modules that we've developed that we've identified as being very important. One of the key things is, and I've heard this on a number of talks here, is the Linux operating system, and that's something that's universal, and it's a great operating system. Everybody can get access to it, and everybody can use it. Some of the other things that are nice is if it's as a web-based software platform, it can be installed in one place at an NDC or at the IDC. You only need to upgrade the code on a single server, not across every PC that's available or that you have in your NDC or university or at the IDC. Data is managed by a server, so you don't need to have user database credentials. Especially for small NDCs, this allows them to be able to access the data from somebody else supporting that server, that database, and download the data and look at it and then upload it again. And then finally, taking advantage of performance optimizations of a web browser. We all know how to use web browsers. We all know the look and feel. We've all become very consistent with those things. So, that opens it up to having a standardized plotting platform. All right. So, to kind of kick this off, we developed a website. It's live. Let's see, hopefully, whoops. Okay, wrong direction. The The website is live, so you can go there. This basically just allows you to read what Watchman is about, what Sentry is about. As we develop more modules, then this would be a platform to be able to spread them out to the rest of the community. So this is just an example of something that we developed. It was early on, it was developed for data quality methodologies, and it was to generate up fake beta gamma data that could be used for testing algorithms to make sure that we were getting the right answers, as well as creating test cases for exercises. So this was used in IFE 14. The fear was that one of the stations or the Xenon systems may or may not work on a consistent basis, so we could generate up data to keep the exercise moving. And so this one is live as well. The link to it is back on the website. So what it does is basically allows you to put in the number of atoms, change some various parameters, and you can generate up your own beta gamma spectrum. What I like about this in particular is that you can do things that are unphysical. So as a test, you create something like a pure Xenon 133M spike. There's no such thing. Xenon 133M decays into 133 fairly quickly. So it's a good test for your graduate students to categorize these spectra and tell what they are versus the physicality of them. Here's another one of the modules that we've developed, and it's just a simple one. It allows you to view the beta gamma data that's generated by the IDC, so you get to have basically just a view of it to see if you've got a hit or not. We'll add into this later on the activity concentrations and calculations as well. This goes back to some of the modules and some of the analysis methodologies that were developed, most of them developed by the FOI and the 10 region of interest analysis methods. So this just goes to whet everybody's appetite on some potential future modules. Data Health Viewer. This is something that was recently provided to the IMS to monitor the radio Xenon systems. Again, it was based on a web-based system or a web-based graphical user interface. And it simply displays the data that's coming in. Once you can display the data, now you can think of ways that you want to analyze that data and then redisplay it. And so that's the brains behind the thing, behind the development is what are those algorithms that you want to develop, put into a platform so that now you can view them and start making decisions based on them. Of course, advanced spectroscopy analysis for beta gamma and gamma spectroscopy. We're starting to see some non-standard radio Xenon isotopes out in the environment. This is something that was suggested many, many years ago. We have a couple of instances where that's actually occurred. Time series analysis of the preliminary data sets. So the preliminary data, every 2 hours a preliminary file is sent in. To my knowledge, no one is really using that to do half-life corrections or to try and tweak the sensitivity and get these answers even better. Although I believe work has been done on that at the research level. Of course, there's different analysis methodologies for radiation detector types. I mentioned silicon. There's many out there that people have published in the open literature and that can be certainly can be integrated in. Of course, they have to be in a system that's out in the field taking data as well as proving their worth. But the idea is that that should not be a major effort to get that analysis into a package of radionuclide software analysis. I put down here WebGrape improvements. I think WebGrape has gone a long way. It is a great piece of software. So advanced atmospheric plume model display. And it's my naive notion of what currently exists out there. I don't know that we've included dilution and washout effects at the IDC if that's been included, but it's just a suggestion. So in summary, Sentry is envisioned as a radio Xenon data analysis platform that provides the IDC with updated radio Xenon data analysis techniques. Obviously, at the end of the day, enhancing the workflow of the RN data analysts is very important. If we go off and we put in more stations, as has been suggested, then that becomes very, very important. We don't want to overwhelm the analysts. We also are at a point now that we are beginning to see the limitations of the analysis that we have been applying for 20 years, and so it is between detectors and the analysis methodologies. Now is a good time to step back and say, okay, what are the improvements that we've done through the years, and what should be incorporated, and how do we take advantage of those improvements? And of course, as usual, export community-driven development and vetting of new analysis techniques is absolutely critical. And so, again, that steps back to the community development of what Sentry is envisioned as, is really a community-driven set of modules that have been proven. So I end with seeking co-authors for a technical review paper to cover improvements for analysis of radio xenon. That's kind of the jump-off point. And I have my contact information, and I would be very interested and happy to work with others and collaborate on a paper that we bring together the best practices for the radio xenon analysis, so that we've got between what we've done in the past and where we want to go in the future, that we've got a good starting point. So with that, thank you.
Thank you very much, Justin. Before I open the floor for questions, we really need to, I think, get our structure for the 1 minute slide presentations going right now. There's apparently 36 of you in the room that will be doing the 1 minute previews. If you can line up in that corner, it will just take too long if you come from the back. So please, as we open the floor, start moving into that corner. I'm not going to try and manage the rhythm from here. As your slide appears, please move to the podium. You have 1 minute. If the 1 minute is finished in the words of one of the previous presenters, it's over. You will have to vacate the podium to make space for the next slide presenter. So thank you very much to the two speakers this afternoon. And if there are now any questions, then please raise your hand.
So my question is to the last presentation.
I could never have guessed.
So this is, despite your several examples, my impression is still a little bit abstract of what this Sentry is. Is it a toolbox for developers, like the root from CERN that we're using, it's like a library of fitting routines and so on? Or is it more a collection or a integration of everything you might want to do with a radio xenon analysis, from spectral analysis onto interpretation and so on? What is it actually?
Well, the nuts and bolts of it are, as you say, I think Root is a very good example of a community-driven development of individual analysis methods. Fitting a Gaussian peak has been done thousands of times, and so you need to have that call, and that call is there. That's kind of the idea, is that we've developed a few of those tools, and of course some of them have already been developed long ago, so we just incorporate them. But a graphing technique or a graphing method in a web-based graphical user interface, we've had to develop our own because the ones that are available openly are insufficient. And so that's the nuts and bolts of it. Now what we do with it, of course, is that we start with what are the methods and the analysis that we already have that we'd like to be able to port over to something that's got to give a consistent experience. And so radio xenon, automated radio xenon analysis would be kind of the first one to go to. All right, we do that. All of that development now allows us to say, okay, now we want an advanced interactive analysis for radio xenon. What do we want to do? And like I said, there have been a lot of papers on things that individuals have developed, and they're great tools and they're great analysis methods, but unfortunately, it's not used really anywhere. And so we have thousands of data files, and I'd love to be able to throw these analysis methods at all of those thousands of data files to say, hey, this technique really works, or we can tweak this technique, and now it becomes something that is an advanced radio xenon analysis tool in our toolbox, and we step on to the next thing. So that's the, I guess I'm trying to say a clearer vision, I hope. So, all right.
Thank you.
There is one
question on my left of the room. The mic is coming.
Great. This is my question for the last speaker again. A great job plugging Linux. It's always nice to see that. On your beta gamma simulation that's available on the web, is there a particular detector that you're simulating there, or is it something that the user can enter his or herself? And then second of all, what underlying simulation package are you using for that? And then finally, if this works well, are you planning to extend to other radioisotopes?
The extension to other radioisotopes, if you do gamma analysis methodologies, there's a number of them. So it's kind of, beta gamma was one of those ones that's very specific to us. So, I'd say if you were going to do gamma, there's some great codes out there, and a lot of them that do a really good job with simulations. On the beta gamma, we picked a very specific detector type. The idea was eventually we could go off and do, as you were saying, pick the detector, pick the schema, et cetera, et cetera. But that became just a daunting task. And again, the driver behind that original module was basically data quality. We needed to know if we threw 100 atoms with an efficiency and a detector that we well understood, did our algorithms give us the right answer? And my fear is not a call from the president. My fear is that the guy who tells the president that a nuclear test occurred isn't giving the right answer, because me and my team came up with bad algorithms that we didn't test thoroughly before we tossed them out the door and that they were used. So that's kind of my fear. It's a step removed, but I don't want to see that happen.
Thank you.
Can I just follow up one quickly?
Sure.
Sorry. So then you're not actually doing any underlying simulation when you give those beta gamma, whatever list mode results or spectra, et cetera. You're using tabulated efficiencies
sorry, I didn't
or
answer
whatever
that
for
part
a
of the
particular
question.
detector then.
We use JONT for the simulation, number one. And number two, it turns out that you can make list mode data from a two-dimensional file fairly easily. So you can use your own data that you had generated up yourself, or not generated, but you had measured yourself, and you can generate a list mode data set with that, which is what we had to do because nobody can do a really good background in a beta gamma coincidence system yet. So.
Thank you.
Okay, I have one question for the first presentation. Yes, maybe go back to the conclusions when you talk about the local scale for the barium and to jump to the global scales. What do you mean exactly? Because I did not catch exactly what you mean on that.
The idea that generally when you produce an ITM, you have, for example, a categorization level 5. So you have a suspicious, then you start with the ITM backward to try to simulate the pathways and to estimate the source location and size. But you are performing this simulation on original data, on raw data. In such data, you have periodical components, you have a lot of structures, not only the original, so the target of your physics. In that case, the target is if you are able to detect the nuclear plume produced by nuclear test from source to receptor. If in your time series you have just a change, continuous change in the periodical signals, let me explain it. If you are tuned with a radio and you are hearing music in the radio, it's always the same frequency. But you can hear better sometimes or not. If you consider that the power station of your radio is always the same, the change in amplitude or in noise at receptor depending to the pathway or locally to the receptor. If you not discriminate all this physical process. When you produce an ITM, you can have an overestimate or underestimate of source location, sites, emission, and so on and so on. The only real data in this mathematical problem that we have are the experimental data at IMS station. So I need to characterize not una tantum, but every day, because the noise structure in the IMS station changing. It's not in ideal lab. So you are performing the same experiment because you have germanium detectors or you have an Ober gas system that collecting, but the lab changing because changing the environmental parameters in the lab. If you not include this characterization, in our point of view, when you cross-correlate at global scale, the final results may be wrong. Okay, global is anyway part of a particular. So.
Okay. No,
so the philosophy today is, of course, to start immediately to global without any information about the particular, but maybe dangerous.
Okay, thanks.
Thank you. There's time for one more question if it's really pressing at this stage. I would like for us to move on to the poster previews. I think what we see here is a reflection of the very exciting and very pleasing reaction we had to the call for abstracts for this particular session. It is only time and space that limited us in terms of the number of presentations, oral presentations, and posters that we could accept for this session. And if there are no further questions, then I would suggest we start with the poster preview. Thank you.
Okay, I'm going to be reporting on work that we've been doing using a 3D visualization capability, building interactive 3D environments to help improve on-site inspection operations, which leads us to think about questions that the inspectors might be asking, such as, where are we going? What might we see on an inspection? Will it look like the photographs? What might we find when we get there and start doing analysis and collecting data? And, importantly, who has the map? So for answers to those questions and others, please come and see my poster. And for answers to even more questions along a similar vein, please come and see my talk here tomorrow morning. Thank you.
In 2005, Hafiz Ghalib and his colleagues, they formed a joint team of American and Iraqi seismologists to install 10 stations in northeastern part of Iraq. And over the years, the network has grown to include an array and then became part of the backbone of the Iraqi national network. The cooperation continues to this day. Every day they jointly process the data. So that area, as you know, is the best site for seismometers because there you can see the hot bedrock and the remaining of Iraq will be just a desert. So this is a first step of the cooperation between the two countries and is mutually beneficial. Welcome to take a look at the poster. Thank you.
I'm Harley Benz, scientist in charge of the USGS National Earthquake Information Center, and we have a poster here that will illustrate the richness of the inputs that we use in our processing system that range from Twitter detections to macro seismic inputs all in real time to classical peaks and amplitudes. The poster will describe how we process this kind of information to produce the wide-ranging products that are well known on our website, from earthquake locations, magnitudes, moment tensor solutions, to financial and loss impact assessments, all done in real time. A key point in what we're doing is we do self-discovering, self-configuration of our system to ensure that we're using as much data as possible to characterize the earthquake source and its effects.
Good afternoon, everybody. So for those of you who saw my talk on Monday, which was to do with data fusion and visualization, this poster is going to go a little bit more into detail of some of the processing that went on behind the scenes before we got to visualization. Specifically, I'm going to be looking at the seismic data and how we go from, raw seismic data to something that you can visualize in a 3D environment of value to the inspectors. Here's just some examples. I'm also going to look a little bit more into detail about the photogrammetry that we did to make a 3D model to input into our software that we've been testing. So come see the poster, it's number P8.
My name is Dave Harris, and there we go. Okay, my poster addresses the issue of template mismatch and correlation detection, which tends to reduce detector performance. So the figure here that I show shows waveforms from the 5 North Korean tests recorded at the one channel of the Warmunga array. And the strong similarity, of course, suggests that we use correlation methods for detecting events at the site. But we also see that there's some variation among the signals which could lead to mismatch when using waveforms from one event to detect the rest. We like detectors to be robust, which means insensitive to target waveform variations, but also sensitive, which requires that they not respond to background noise. The correlators as currently used are sensitive but not robust. So my poster describes 2 detectors that generalize correlators to be more robust by allowing more degrees of freedom in the waveform template. The 2 are subspace detectors, which you may be familiar with, which are more robust than correlators but less sensitive, and a new type, tangent space detectors, which are both robust and sensitive. Thanks.
It's the first.
I'm number 12. I'm Peter Gebler from the German NDC. This is not my slide number P12, please. And we try to, our poster gives an estimation of the global detection capability of the IMS seismic network in 2013. The method is based on measurements of the ambient seismic noise field at the individual IMS stations, as well as in global distance correction terms for body wave magnitudes that are calculated with seismic reflectivity method. Of course, as already mentioned in the panel discussion earlier this day, there have been plenty of studies and publications on the topic of detection capability estimation. But nevertheless, we try to give some more information about dependencies of the detection capability, in special about spatial parameters, temporal parameters, and many other parameters. So for more information, come see my poster.
Hello, my name is Matt Goodwin. I work at the UK NDC for radionuclide analysis. The poster is on how we've developed our techniques for automatically analyzing all of the data. So we've incorporated our own code for beta gamma analysis called BGAX, and we utilize Canberra's Genie 2000 algorithms for automatic analysis of the gamma spec as well. So come along and see the poster.
Hi, I'm pleased to present this poster on behalf of my colleague Olivier Dolon. So today's situation in gamma spectrometry is almost the same as in photography 20 years ago, when we progressively changed from silver photography to digital one. The digital electronics opens a new field of opportunities for gamma spectrometry. It has plenty of advantages, like you can manage coincidence, do some timestamping, waveform capture, pulse shape analysis, and many things. But of course, there is also a price to pay for this. So the poster will come back to the advantages and drawbacks of this model, of these methods. So enjoy the visit to the poster. Thank you.
Hello, I'm Carol Johnson. I'm Chief Innovation Officer at Introspective Systems in Portland, Maine.
Although we have deep experience going all the way back to the very origins of digital network operations, our current focus is more general, and we like to look at problems of limited resources that need to be optimally distributed. We use a tool called XGraph, which is a fractal executable graph framework. In terms of seismology, the way this applies is you have to imagine that the data is the resources, and the analytics, the high dimension decision space, is how those are applied to a limited set of events, and how those phases are, for example, identified. If you can imagine waveforms picking themselves, earthquakes locating themselves, and a catalog that emerges as a self-organizing criticality in the sense of complexity theory, come and talk to me if you're curious or skeptical. Thank you. Like to see you at P15.
Okay, good afternoon. I'd like to present this poster on behalf of my colleagues from the United Kingdom National Data Centre. And this is looking at evaluating clusters of infrasound-only events in the reviewed event bulletin, which is a product of the International Data Centre. So there are 4 large clusters of infrasound-only events, and we're looking at the reliability of arrival identification using an independent detector as an objective measure. And it turns out that the event definition criteria require at least 3 detections at infrasound stations, and it turns out that only about 60% of the events analysed in the clusters meet that. And it also turns out that looking at these clusters, that the sources of infrasound network events very sensitive to higher elevated sources, such as those from aeroplanes going supersonic a few kilometers off the ground. And it turns out the geographical distribution of event locations is seasonal, and this is dependent on the stratospheric winds, which blow in different directions according to the time of year. So that's poster 16.
Hello, I'm Ben Baker. I'm going to talk about some ongoing work with the IDC and ISTI. It's related to primarily pulling out depth estimates. So I'll start with the cross-correlation driven methods. I'll move on to waveform fitting methods as I jack up the model space. So I'll start doing moment tensor estimation. And then I can start talking about just how different data sets help resolve the higher parameter space, and particularly which model parameters I can and cannot resolve. And lastly, I'll talk about the GUI for driving the workflow. Thank you.
This poster again about waveform cross-correlation. It studies the scale from the biggest aftershock sequences like the Hoku down to the smallest aftershock of the DPRK5, which is about magnitude 2. All of that is possible by waveform cross-correlation with very accurate locations of all events detected and found in the sequence, or just one of them. Thank you.
Hello, I'm Mikhail Roshko from CTBTO. We made an approach to create the frameworks for building multidimensional subspace master events, embracing most of the IMS seismic installation, and try to estimate benefits it can bring to cross-correlation based relative location methods. So we regarded signals from 3-component stations as 4-component hypercomplex vectors, and the data from more complex seismic installation we regarded as multimodal tensors. And then we applied hypercomplex and multidimensional tensor dimensionality reduction methods to extract the templates used later on in further cross-correlation based relative location methods. So we successfully tested these methods on Quarry blast data from 3-component station and arrays. So welcome to poster number 20.
I'm Elena Tomuta from the IDC, and I'll be introducing the first of 3 posters that describe the IDC re-engineering project phase 2, This is work that was supported by a team from Sandia National Laboratories, and it's a project that ran between 2014 and 2017, was completed in April this year, and it develops a new architecture for SHI software as a whole that is intended to support the IDC for the next 20 plus years, and we hope will be implemented in a third phase of IDC re-engineering. There are two more posters related to this project that deal with particular aspects of the project, and I'll go ahead and speak about the next one as well, if I can change the slide. Sorry. So the first of these two specific posters deal with analysis interface improvements designed in this new architecture. And I think it's a very interesting poster to consider because it brings a couple of improvements for analysts' work. And you'll see that the poster contains a lot of mock-ups of screens and functionality that could be provided to analysts while keeping the basic idea of the analyst interface and tools the same as it is now. So I look forward to talking to you more about this. Thank you.
Hello, my name is Helmut Breitenfellner from the IDC, and I have the honor to present the third poster of this re-engineering project, which highlights on the architecture and the data model. You will also see some information about the prototyping, which has been done in the IDC to test the feasibility of the approach. Thank you.
Good afternoon. My name is Mahmur Ezgerkan and I'm a research assistant at Kocaeli University. My study is about the importance of noise levels at CTBTO facilities. As we know, seismic noise exists everywhere on Earth's surface, and it affects our quality of data. We analyzed seismic background noise analysis of BRTR array, which is one of the IMS stations, and 6-year data were calculated by the power spectrum density and probability density function, and the results show us a little noise changes in terms of time and location. Thank you.
Hello, I'm from CTBTO. We have been developing a new automatic seismic event detection and localization program. Even though it shows better performance than our current one, we need to be very careful to install it. At the same time, analysts want to use the net visual data because it's better than our current one. So we have developed an environment which provides with analysts with net visual data, which also doesn't break anything in our current configuration. In our sandbox testing, it shows a promising result. Thank you.
Okay, so here we have a classic good quality event with good signals in a range of azimuths, well located, and then we have this close-in observation, close-in station with no signal. Classic case of negative evidence showing that the event is either a false event or probably badly located. Now, this kind of thing is what analysts deal with every day, but it's much more difficult to deal with this in automatic processing because we have to be very certain that the non-observation is really a non-observation and not just absence of data or absence of a few samples of data, meaning the detector can't work. So this poster has a few things to say about that topic.
Hi, I am Yamba Kassoum from Burkina Faso. This work presents a new promising approach using nuclear event timing to discriminate, to identify a nuclear explosion signature from other nuclear events like nuclear power plant release. we was able to identify with very good precision US underground nuclear explosion from Nevada test site displayed here. We were also able to identify with good precision Fukushima accident release. I will be very pleased to discuss more with you about our results. Thank you.
Hello, Lee Glasgow, Lawrence Livermore National Laboratory. It's my pleasure to present to you a poster on optimizing atmospheric sensor networks to minimize uncertainty using Bayesian and genetic algorithms with multiple objectives. An example analogous to treaty monitoring is discussed in detail. This example is the design of greenhouse gas sensors in the state of California, optimizing on two competing objectives, sensor performance and deployment cost. I look forward to seeing you at my poster.
As a research project, Lawrence Livermore National Lab installed seismic arrays in the Middle East. The arrays are identical in design. They are a small aperture, 9-element, 3-component. The equipment and the deployment provided by the local institutions, King Saud University and Earthquake Monitoring Center in Oman. We analyzed this data to identify the noise sources, magnitude detection thresholds, and also correlation detections. We see some variations, azimuthal variations of events detected from east and western part of the Arabian Peninsula. Thank you.
Good afternoon. My name is Neil Wilkins from Bristol University in the UK, and I've got a poster presenting some work I've been doing developing some corrections for IMS seismic arrays. The first sort of correction are corrections to the slowness and azimuth, and the second are static corrections to the arrival time and the amplitude. And I demonstrate some improved signal-to-noise ratio at some earthquakes recorded at IMS arrays. So if you're interested in that, please come and visit my poster. Thank you.
I am Chandan Saikia from Air Force Technical Application Center, United States. Here we have developed a technique in which we prune the complex spectrum for partitioning the waveform for upgoing and downgoing wave field. And what we do that we try to use the concept of minimization of phase, but in my case, it is minimization of unwanted phase. It could be either upgoing or downgoing. And we also looked at whether real capstone is better than complex capstone, and I will have some answers there. I also looked at the time sampling, whether 100 samples per second versus 40 samples per second, so we'll be able to give discern the interaction between little p, big P waves at large distances. So I'll be able to discuss the mathematical background in my technique and give you some initial results of blind test and some tests where we used theoretical upgoing, downgoing wave field as some template. Thank you.
Hi, I'm Ilana Tibulak from the Air Force Technical Application Center. In addition to Dr. Sarkia's poster, the AFTAC team under the lead of Dr. Kemerit has 3 more posters this afternoon, 2 on applying advanced signal processing methods to existing capstone algorithms, and 1 on applying seismic interferometry to ambient noise and teleseismic events to find out the depth of cluster layers. In the poster, which is shown here, we discussed the benefits for depth resolution of shallow events, of course, when using higher sample rate, and how to overcome the increasing capstone noise, which also comes with higher sample rate. So come over and we're gonna talk about it.
Hello everyone, I'm from Beijing Radionuclide Laboratory.
it's well known that nuclide monitoring play an important role in CTBT. Generally, a particle sample were measured on the surface of high-purity germanium detect. Under this circumstance, the coincidence summing effect is inevitable. Our post, the mechanism, influence, correction method, and correction scales were introduced. Welcome to browse through and discuss. Thank you.
Good afternoon. In this poster, we present a method for automated analysis of infrasound detections, which is based on data fusion of EMPs, electromagnetic pulses, and infrasound. We show how to identify and remove EMPs coming from lightning discharges, and then use the existence or absence of the nuclear EMP in order to verify the treaty relevance of the triggering event. I'll be glad to provide more details by the poster number 48.
I'm an imposter for here. This is a collaborative work between Florida Institute of Technology in Melbourne and FTech, Dr. Dean Clouter. And they are looking at here time series classification towards identification, and given an event or time series, they extract some features, then build a covariant matrix. From the covariant matrix, try to identify the classification where it belongs. And they claim that covariant matrix formulation does better than any other formulation they have tried. So I'll try to explain. This is not my field, but if you come, probably we can learn it together. Thank you.
Right, so you've heard a lot about the IDC re-engineering project for the next 20 years. This poster's about something that is not envisaged in the re-engineering project. That is a paradigm shift in the waveform analyst user interface. All the software available for global analysis of global data, it really evolved from the idea of paper records and how things were done in those days. So this poster is offering some ideas on how to proceed beyond that paradigm into something different. And rather than describe now some of these ideas, I suggest you come to the poster.
Good afternoon. My name is Rong Song Ji from State Department of the United States. Last year, the Navy carried out a series of full-ship shock trials off Florida in the Atlantic Ocean. And we took this opportunity to evaluate the networks operated by U.S. Geological Survey and the one IMS. It turns out that both networks operated as expected. The events were well recorded in eastern United States, about 130 stations. And then the teleseismic IMS stations, they also recorded the event and reported. IDC didn't screen out the events. The Navy kindly provided the ground truth. For us, that's a precious calibration opportunity. And there are several teams started doing some research to check several algorithms. So that's poster number 52. Thank you.
Hello, this is Monica Galan from CTBTO. Nuclear and decay data are well used in theoretical and applied physics. Here we present the latest evaluation on nuclear and decay data of the 4 radioxenons of interest for the CTBTO. The evaluations have been made under the Decay Data International project group, and this includes the most recent measurements on these radionuclides and the ultimate computer tools used by evaluators. The evaluations results are published through the DDEP website, and in the poster we also present the differences found with the nuclear data stored in the CTBTO nuclide library. So we recommend an update of all nuclei library. Thanks, and for more information, visit my poster. Thank you.
Good afternoon. My name is Yuri Dubasov from Klopin Radium Institute, St. Petersburg, Russia. We proposed a measurement model using random variables coefficients. Their numerical characteristics depend on measuring cycle duration, and they determine the bias and additional uncertainty results. The model takes into account decay and accumulation of xenon radionuclides depending on time of their stay in the adsorber. The model does not limit on variation of xenon radionuclide. Thank you.
Hello, everyone. I'm Viviana Dionisio from the Colombian Geological Survey. I want to show you a little bit about us. So we managed the Colombian Seismological Network and the Strong Motion Networks in 1993. And I want to show you how we release our information. So we have earthquake information with two different automatic locations. We have the manual location. We also have shake maps and intensity maps, filling out the, did you feel it? And we also manage a little bit of the seismic hazard and history of studies of historical earthquakes. So if you want to see a little bit more, please visit me in my poster. Thank you.
Thank you very much. I think we should really give all the speakers a round of applause for a very well executed poster preview. So before we close this part of the session today, let me remind you that we will be back here at 9 o'clock tomorrow morning. We have 6 oral presentations to go through, and in the afternoon another 3. That's tomorrow afternoon at 2 o'clock, which will be our last part of the session. Then I was also asked to remind all of you to please cast your votes in terms of the best poster and best oral presentations. There are 2 ballot boxes. The one is up front here. You're welcome to use that, and if you can't get to this one, then there's also a box at the at reception downstairs. So please remember to at some point go drop your ballot paper into one of these boxes. Thank you very much for your attendance in this session, and I hope to see you all back here at tomorrow morning.
Tomorrow morning. Okay.
Thank you.
Thank you.